In chapter 4, we are going to learn about how to take the derivative of exponential functions and of log functions. So we first need to review exponential and log functions. In this section, 4.1, we're going to look at exponential functions. And 4.2, we're going to review log functions. And then when we get to 4.3 and 4.4, that's when we're going to start doing the calculus stuff of finding the derivative of exponential and log functions. In this lesson, we're just going to focus on exponential functions. So when we look at an exponential function, it's in this form, although I don't like the way this book does this because there could be a coefficient in front. So keep that in mind. You could have a coefficient, let's call it a, times b to the x. So keep that in mind. B has to be greater than 0, and b cannot be equal to 1. The reason why we don't want b equal to 1 is because if we have 1 to the x, no matter what we plug in there for x, our answer is going to be 1. 1 to the fifth is 1, 1 to the negative third is 1. So that would no longer be an exponential function. That would be just a horizontal line, a constant function. So it's not really that b cannot be 1, it's just that if b is 1, it's no longer an exponential function. Okay, now a lot of students have issues with distinguishing the difference between power functions and exponential functions. So I'm going to try to make it real clear right here. When we look at a power function, think about a polynomial. We have the variable, which is typically x, raised to some power, like x squared is a quadratic, x to the third is a cubic. So our variable is our base. When we have an exponential function, our variable is going to be in the exponent. So down here, you're going to have some constant, and then it's going to be raised to a variable. Let's look at our first example. We're going to use tables to graph f of x is equal to 2 to the x and g of x is equal to 1/2 to the x. So if we use the x values to make our table from -3 to 3, keep in mind that these are not all the x values, right? There's infinitely number x values. We're just choosing to focus on -3 to 3, those integers. If I plug -3 into the function 2 to the x, I would have 2 to the -3. The negative in the exponent means to take the reciprocal. And if I take 2 to the third, that gives me 8. And then I take the reciprocal because the exponent is negative. So there we have 1/8. When we plug in -2, we're going to get 2 to the 2 is 4. But because our exponent is negative, we take the reciprocal, which gives us 1/4. Okay, so when we go through and plug that in, we're going to get these values here. Now notice when we get into the positive values, we don't take the reciprocal because 2 to any of these numbers, 1, 2, or 3, those exponents are positive, so we don't find the reciprocal of the base. Now for this function, I have 1/2 raised to the power of x, and these are very, very similar. The only difference is that this is going to be an increasing, the 2 to the x is increasing, and the g to the x is decreasing because this base is less than 1. And we'll get into that in more detail here in a minute. When I start plugging in values here, if I plug in -3 here, the negative tells me to take the reciprocal, which would be 2, and then take 2 to the third power, that's 8. If I plug in -2 for the x, the negative tells me to take the reciprocal, which is 2, and then raise it to the power of 2, which is 4. So now looking at the graph, the 2 to the x, when we plot those points, we get an increasing function. And then when we graph 1/2 to the x and we plot those points, we're going to get a decreasing function. Now, some things I want you to notice about the graph. If you have an exponential function and you don't have a vertical shift. In other words, I don't have b to the x plus or minus some constant over here that causes us to have a vertical shift. If there's no vertical shift and it's just b to the x, then we're always going to have a horizontal asymptote on the x-axis. And this is going to get closer and closer and closer to the x-axis, but never theoretically touches it. Same thing over here. We have a horizontal asymptote. Now, if I added a +1 to this, that means I have a vertical shift. So now instead of having my horizontal asymptote here on the x-axis, it's going to get bumped up one, and my horizontal asymptote will be at y equals 1. So here's some general information about exponential functions. If you have b to the x, and keep in mind, you could have a coefficient in front here. They should have put that in there. But if you have b to the x, if b is bigger than 1, if your base is bigger than 1, then it's going to be an increasing function, meaning going left to right is going to increase. If your base is between 0 and 1, that's going to be decreasing. So b could be 1/2, 1/4, 2/3, something. It could be 0.75. This b needs to be between 0 and 1 for it to be decreasing. Now, here is a very famous number. It's called e. It's the natural constant. This is similar to pi, where pi is 3.1415, and then you have a whole bunch of digits, and it goes on forever, and it's irrational. E is similar to that, but it's just a different number, but it's an irrational number that has infinite digits. The way mathematicians discovered the number e is with this limit here. And you might recognize this function here. If you've done financial formulas with compounding, this is very, very similar. But if you take this limit as x approaches infinity of this function, you will get e, the natural number. Notice as x increases, because we're going to positive infinity, so we want to keep getting bigger and bigger and bigger, we can go out to 500,000 here or 1,000,000. But as we get bigger and bigger, this number is going to approach the value of e. Example 2, we have graphed the curve e to the 0.3t and e to the 1t and e to the 3t. So we'll be using t is equal to -2 to 3, and these will all be our corresponding values for the dependent variable. When we compare these three graphs, we see our bases are the same, so the only thing that changes from function to function is the exponent. As the exponent gets larger, so we have a 0.3t here, and a 1t here. So this, if I plug in, say, 7, is going to be bigger than this one. And then this one's going to be even bigger. It's going to be double that one. So when you look at the exponents as they grow, the rate in which the function increases grows. So it's going to go up faster and faster. And the same thing happens for if the constant is different, but the exponent is the same. So let's say this is 2 to the x. Let's say this is 3 to the x, and let's say this is 4 to the x. The 4 to the x is going to grow faster as opposed to the 2 to the x here. So on this page, we just have some features about the behavior of the exponential function. Now here they actually put a coefficient in front, so that makes me happy. In this case, they're using the base e, so that's our constant, the 2.718, that irrational number. And then we have kx and -kx. One of the properties of an exponential function is that the domain is all real numbers. You can plug in anything you want for your x, and you're still going to get out some value for y. It could be super, super small, and it could be super, super big, but you're still going to have a value. So your domain is going to be all real numbers. However, the range is not going to be all real numbers. If I have a positive exponent, then I have a horizontal asymptote at y equals 0 on the x-axis, and as I go left to right, it would be increasing. So it would never go below the x-axis. The same thing goes for if you have a base raised to a negative exponent, it would just change direction. It would flip over the y-axis. So it would just be decreasing from left to right, which means since we have that horizontal asymptote and it flattens out, it's never going to drop below the x-axis. So the domain, unless you have a vertical shift, the domain is going to be all positive numbers. It's not even going to be y equals 0 because for that horizontal asymptote, the function never touches the x-axis. The exponential functions are continuous. There are no holes, jumps, or vertical asymptotes with an exponential function. Both functions are going to pass through the point 0 and then whatever your coefficient is. So where the exponential function crosses over the y-axis, this coefficient in front will always be the y-intercept unless you have a vertical shift. So here's the reason why. When we have a y-intercept, that means it's the value of y when x is 0. So if I plug in x is 0 either here or here into the exponent, we would have e to the 0 on either case, and e to the 0 is going to be 1. And then I would be left with this initial value, a times 1. Same thing over here, a times 1. So when the value of x is 0, the value of y is going to be this initial value here, which means it's always, this value here is always going to be your y-intercept. And the last thing, and we kind of already talked about this, if you have a positive exponent, then it's going to increase. If you have a negative exponent, it's going to be a decreasing function, and that's what it's listed here. Okay, now let's get into applications of exponential functions. Imagine that a particular time, a kitchen counter has on it 5 bacteria, and that this type of bacteria doubles in number every 10 minutes. So 10 minutes is what's called the doubling time. The exponential function 5e to the power of 0.06931t is a good model for predicting the number of bacteria in t minutes from a particular start time. How many bacteria could be predicted on the counter 2 hours later? Now, this one's a little bit tricky because they switch units on you, and you really have to pay attention to this. Since t is in minutes, right? It's talking about minutes, and they give you 2 hours. If t is in minutes, you have to change hours into minutes before you plug it in. 2 hours is 120 minutes. So we would plug in 120 for t in here and then evaluate that. So we would get 20,468,000 bacteria. And that would be 2 hours or 120 minutes after the starting initial value. This 5 is the initial value, and they tell you in here that that's where they start. It has 5 bacteria on the kitchen counter, and then they start taking time. So this is what I was telling you about. This is always going to be the y-intercept. And in terms of an application, the y-intercept is going to be the initial value because it's the value of the dependent variable when the independent is 0. So at time 0, if I plug in 0 here, I get e to the 0, which is 1, and 1 times 5. So that gives me a starting value of 5. In example 6, we're going to look at an application involving compounding. The A here, or the output, is your accumulated balance, and that means whatever you have left in your account after the specific time interval, and that would include the money that is deposited as well as the interest. The P in this formula represents the principal, so that's your initial deposit. And as you can see, that P is in front, which is your y-intercept, like we discussed before, or your initial value. So in this case, we're talking about our initial deposit. The R in this formula is your annual percentage rate as a decimal. So if the annual percentage rate is 8%, we would put in here for R 0.08. N represents the number of times it's compounded a year. So in this case, we're going to talk about compounding quarterly. So our N would be 4 because it's 4 times a year. Then your exponent is going to be the total number of times that this is compounded over the entire time frame. So in this example, it's talking about doing this for 15 years. And since it's quarterly, that means 4 times a year for 15 years. That means this exponent is going to be 60 because you take 4 times 15. So the question says determine the amount of money accumulated after 15 years if 2,000 is invested in an account that pays 8% interest compounded quarterly. So we're going to plug in all that information. Now with this formula, your time, which is your number of years, is your input. So when we set this up using function notation, your t is your input for 15 years. So P is our principal, that's our initial value or our initial deposit. 0.08 is our APR, compounded 4 times a year, and then a total of 60 because we're taking 4 times 15. Now, if we wanted to write this as a function where we could plug in any value of t, we would leave the t there without plugging in the 15, and that way you can plug in any number of years. Now, once you evaluate this, you're going to get $6,562.06. And what this means is that after 15 years, given all the information, we would have $6,562.06 in our bank account. Now, because we deposited 2,000, that was our initial deposit, and this is what we have left at the end of the 15 years. The difference between the balance and our initial deposit would have to be the amount of interest that we've earned. One common error that I would like to point out is that when students evaluate this, a lot of times they'll work the inside first and make this a rounded decimal. However, a lot of times this doesn't work out so that it's a remainder 0. And you'll have a lot of digits that follow. So in this case, it works out nicely. 4 goes into 0.08 evenly without a remainder, so we're not too concerned about it here. But what I'm concerned about is that if you work this step first and you put that in parentheses down here and you round the decimal, each time you complete your step, you're doing that with a rounded decimal, and it's going to probably throw your answer off. So what I would suggest is to put all of this in your calculator and do it all in one step without making rounded steps each time. That way, you're not worried about rounding errors. Okay, our last topic is called the logistical growth model. Here's our format for the logistical growth model. This M represents I guess you could say it's your horizontal asymptote. This here is what your graph is going to get closer and closer and closer to as the value of t increases. This is what the basic shape looks like for a logistical growth model. It's going to start off and increase pretty fast, and then at some point it's going to start to level off. And that is going to be where your value of m is. So in this example, your value of m is 5, which means that's where it's going to level off here. Your t represents the amount of time that has passed, and your k is the growth constant. So let's work through an example of a logistical model. Let us model the number of automobile sales in a developing country as, so this represents the number of sales, then our M is going to be 156,000. So that's where we're going to assume that it levels out. Our growth constant is 0.8. And then we're doing this so that t is greater than or equal to 2010. So this is where we're going to start at year 2010. In part A, we're going to look at how many cars were sold in 2010, how many cars are projected to be sold in the year 2015, and then part C says, if the model holds well into the future, at what level will the sales of cars stabilize? So for part A, we want to see the value at the beginning of this time frame. So since we're starting at 2010, we're going to put in 2010 for t. Because this is our initial value, that means the difference here is going to be 0. That means 0 time has passed since this is our initial value. So this is going to be 0. If we keep carrying everything else down, then that will give us e to the 0, which is 1. Keep carrying stuff down. And then we end up getting 156,000 and then over 1 plus 5.6. And when we evaluate that, we get approximately 23,636 cars that are sold. Now, using that same process, we want to see what the estimated sales would be in 2015. So that means we're going to put in t is 2015. That's right here. And then when we subtract, that would give us 5 years that have passed. And then when we evaluate that, we get 141,488. So that means in the year 2050, if the model is a good model, we're going to estimate that the number of cars sold will be 141,488. Now, if the trend continues, t will increase without bound, but it's going to stabilize at a certain value. And based on the definition of our logistic function, that should be this top value right here, our m. But if we look at it in terms of limits, if we want to go way far out for t, we're going to take the limit as t goes to infinity. So that means we're going to start at 2010 for t, and then we just increase without bound. If we think about t growing without bound in the positive direction, that means this t here is going to get bigger and bigger and bigger. We're going to get huge values in here. This here is going to decrease without bound in the negative direction because this, not that infinity is a number, but this is going to grow infinitely large. And this negative means it's going to go in the downwards direction, which means this is going to be 1 over this value of e raised to really, really large numbers. So this here, this e is going to approach 0, which means I have 0 times 5.6 is 0. So on the bottom, I have 1 plus 0, which gives me our maximum value of 156,000. So that's where they're getting the m from. And of course, you can look at the graph and see that that's where it levels out as t increases without bound. We would conclude that if this model holds true, that way in the future, we can expect the number of car sales to level out or stabilize at 156,000. So the last slide are your conceptual questions. So after you work through your homework assignments, come back and just do a self-check to see if you understand these questions.